Okay, natural ventilation. Sometimes all you need is a breath of fresh air. This out of the way. So the definition of natural ventilation is to supply air into a space without any mechanical assist. No fans, no pumps, just relying on the natural characteristics of wind, airflow, heat stratification, convection, sometimes radiation. There's many different ways to approach natural ventilation. We're going to go over some of the basic ones today. This example here shows a bunch of things. It can a system can be as simple as windows to the exterior, perhaps a transom window over an interior door. Is there anyone who's not familiar with a transom window? Can't tell. Okay, just let me know if you are. They're historical. It's an interior window over a door that is provided to allow ventilation from one space that is typically on the exterior of the building into a corridor or perhaps another interior space. Sometimes they're also used for daylighting. They originally started mostly for air ventilation. This example here is also showing a chimney with a stack effect to release hot air out of the building. The stack effect is relying on hot air rising and cool air falling. Looking at wind directions, where the wind's coming from, how do you capture that? These are all different parts of different natural ventilation systems. They're not all necessarily the same either. You can combine different techniques together based on what your design is, what your location is, and how you want to approach it. So there's many different terms out there. Natural ventilation is sort of the umbrella term that is just talking about airflow, creating ventilation, typically cooling, and then there's specific applications that have other names, such as a wind chimney or a wind tower. Solar chimney is often used. Evaporative cooling tower, that's adding in the humidity aspect. We saw a couple of examples of that last week. There's no main right or wrong definition for many of these systems. It's basically how you approach it and which direction you're using it for the wind direction, because there's a tower can do two different aspects. It can either pull air up out of the building for cooling, or it can bring cool air down into the building to cool the interior. Keep in mind the stack effect, where hot air flows up and cool air flows down. Typically, the cool air is slightly more humid, but also makes it fall down and create that cooling effect. So for upward versus downward direction of airflow, direct airflow downward, bringing it in from an opening up high, because you're bringing it down into the building. Example of a courtyard is an example of this. Some wind chimneys or wind towers We'll do this also. If you have direct airflow coming downward where you're adding that humidity assist, you get that evaporative cooling effect or evaporative cooling tower. Direct airflow upwards via wind assisted temperature gradient is that stack effect where as the air gets hotter and hotter, it rises up. And as it rises up, and as long as it's allowed to escape out of the building, it's going to pull more air in at the bottom. You can also add a solar assist to an upward system where in either using dark materials or glazing or somehow adding, utilizing the solar gain from the sun to help heat up the air as it's exiting the building. It makes it even warmer, and so that will pull up even more air. Sometimes those systems are called solar chimneys. So downward airflow often relies on the prevailing wind. Keep in mind, prevailing winds can change at different times of year. There's many different ways to capture the wind, to capture it, bring it in, and then up. So this would be bringing downward airflow in, but then a combo system with a stack effect with hot air rising up and out of the space. Typically, if you're bringing air in and you're doing downward flow, you're going to need some space for that air to circulate, either a fairly large interior space or a courtyard, but you can't have, you need, the spaces need to be connected, and you can't have, it doesn't work real well with a lot of closed off rooms. But sometimes that's why transoms will be added over doors and interiors, that if you do need some privacy, that can still, and you can still open the transom, that can still assist with the airflow. So a couple of examples of this type of a wind chimney or wind tower. It's been used for centuries, particularly in the Middle East. In Persian, the Bagdir towers are a type of wind chimney, meaning wind catcher is the origins of the word. And there's still many examples, historic examples out there that are still existing. Oftentimes, a wind chimney is combined with high thermal mass that's creating, keeping the heat out at the lower levels, and sometimes it's combined with a fountain or water to add that humidity into the air for that that cooling sensation. Sorry, I'm struggling with my mouse today. Okay. A couple more historic examples. Old hieroglyphics in Egypt often would depict a natural ventilation or a wind chimney type of source. These two lower drawings are from hieroglyphics. I don't know exactly which tomb. Or this is another example in Iran, in a desert climate with a combining a dome and a wind capture. So the wind can come in, the dome provides the circulating space for that air inside. Now, if your prevailing winds are constantly coming from the same direction, you can face your openings in that way, or you could have them on multiple surfaces or different facades going around your chimney. We looked at this building a couple of days ago for the passive, the Trome wall that was in this building. This is the Zion National Park Visitors Center. So at the location, where is Zion? Utah, Idaho, I forget which state it's in. It is a desert climate there, so it gets super hot in the summertime. So part of their design incorporates this, what they call a passive air cool tower, where they're using, and I'm going to see if I can start drawing here. They're using a weather vane to help direct the scoop that's going to capture the air to bring it into the building. So this is a downflow system. As the weather vane spins based on the direction of the air, it turns that scoop to the correct orientation. Then here, they're adding some evaporative cooling with some cooling pads with a water element. Now, this is not a true passive system here because they've got a little pump here to help with that, the evaporative cooling system. It's similar to, and this is one way I always remember these misting systems. If you think of the produce section in the grocery store, where you have all the misters above all the produce on the shelves or the coolers around the sides, they remind, some of these systems remind me of that. In this one, it looks like they're actually applying that moisture to some suspended vertical pads that as the hot air passes over it, it will cool down and then fall down to the ground, collecting that extra water from the condensation as it drips from those cooling pads. So then here is the space in the, do I have the circle? Yeah, big space for the circulation. And then again, they're utilizing another weather vane to direct the output of the air. So the hot air is captured, comes in, it's cooled, it falls down. As it's circulating through the space, it starts to heat up again, probably from the people in the building, some daylight coming in. It's just gonna start heating up, probably some radiation coming through the walls to a certain degree. So as that air heats up, it then is exhausted at the other side. Okay. In addition, for this project above the Trome wall, they have, the building has more operated clerestory windows that will also let, where is it? The clerestory windows also allow additional air to come into the space and circulate, in addition to the their cooling tower. And I believe these are mechanically operated. It says yes. It has a computer assist that is, okay, someone wanted in, or they left. If there's someone waiting in the waiting room, you guys, I don't see him right now, but let me know if you see someone. Okay, sorry, this is keep getting distracted. Okay, so combination system with the cooling tower, the operable clerestories, large space to circulate, still needs to have that exit for where the air is going to exit out of the building. Not 100% passive because they've added a little bit of the pump for that evaporative cooling aspect. And then it's controlled by a computer system that's kind of acting like a giant thermostat, but instead of turning on or off mechanically cooled air, it will open or close the windows. Okay, and we've already discussed the Trome wall in this project, and there's an active solar array. Okay. Okay. Opposite of the downflow system is upflow system. Again, there's many different ancient examples of this. This is another Persian method that uses a underground cool air canal or air passage chamber, possibly with some moisture in there. And it's called and I forgive my pronunciation, my Persian is not the best, but a kanat is the name for that underground passageway for the air. This is a really interesting system here where it's relying on a couple of different techniques. So the wind is hitting the side of the tower, but this side is solid. It's not trying to bring the wind in from the top, but this is going to create a negative pressure on one side. Meanwhile, the hot air is going to be pulled down through a shaft into the canal, and pass through that cooler air. But because of the negative pressure on the prevailing wind side, as that cool air heats up, it's going to be pulled out of the top. Excuse me, I said negative. I meant positive pressure on the prevailing wind side. It has negative pressure that's going to help pull that cool air out of the top. Now, this is a circular system, and you're wondering, okay, so what's bringing the hot air down into the into this access tunnel or access column? Well, it's the negative pressure on the opposite side of the prevailing wind that is, because this is sucking air out, it's going to pull, that air needs to come in from somewhere. So that's what causes the hot air to be pulled into the system. So everything has to work together in one giant circle. There's like no beginning and no end, that it all is dependent on the various different components of the system. Don't have a picture of a building that does that, but it's they're located in desert type climates, particularly the Middle East. Now this is another really interesting ventilation system. This is another fun one. I really like this one too, because this is based on looking at the ant hills of in Africa and how they work and how they stay cool. So this is a building in Zimbabwe. It is this double building here with a giant atrium space in the center. So that giant atrium space is, or actually the two massing parts of the building on either side are replicating the anthill. Each side of the building is made up of a series of rooms that have different components to bring the air in. So they've got a shaded solar place on the outside with vegetation that as the air flows across the vegetation, it's going to cool down, it's going to come into the room. Now it also has its exit, it has to be able to get out of the space. And again, this is going to help if air's being pulled out as it gets hot, it's going to pull more air in through and across the vegetation. Then in the whole building together, there's a series of vents that collect all the hot air to go up and exhaust out of the space. And then there's this, the cool air in a separate series of shafts in the atrium space in the middle that is shaded and protected. Cool air is allowed to be brought up and also exhausted out through the top of the building. But it's keeping the two columns of exhaust air separated. So this is the next slide's another example of how this is working. So either side are the two simulated ant hills with the vegetation on the outside where air is allowed to be pulled through. Cooler air in the shaded atrium space, which is also acting like a courtyard. We looked at a couple of courtyards. It was last week where because they're shaded and they create a cooler space within the building. This one, I don't believe there's any water in the middle of this one. I don't believe there is. So cool air gets pulled in. The hot air that gets pulled through the spaces gets exhausted out the top. And the cool air as it rises is, that gets smaller and smaller versus the hot air gets bigger and bigger to be exhausted out of the top. You guys have any questions so far? Nope. You guys still awake? Maybe somewhat, a little bit. It's so hard because I can't see you in class. I can tell if you're falling asleep if we're in the classroom together, but I don't have any good jokes about anthills other than I just think this is just the most interesting design. Okay, wait, back to, so one of the things we were talking about a little bit earlier was prevailing winds. This is an example of a windrose chart. It's based on, or the concept of the windrose is based on the cardinal directions, which also used to be called a cardinal rose for back from the shipping and sailing days. Now this one is for city in Northern California. It doesn't say it on there, but there is one circle for each month. You can see we got January, February through December. And what you're seeing is the frequency of the amount of air coming, or wind coming from a certain direction. So north is up, south is down, east and west, just like a cardinal direction. the standard Western interpretation of the four directions. So in January, the concentric rings show the volume of how many hours the wind is coming from that direction. So in January, there is more wind. This volume is 20. So there's a little bit of frequency of wind coming from here, from the south. By April, that prevailing wind has shifted a little bit to the northwest. And then that looks like it stays fairly west through April, May, June, more westerly winds, not as strong a volume because they're not reaching the outer circles as much. February is a much more windier month with more wind coming from the south. So then through the spring and the summer, wind dies down mostly from the west. And then in the fall, it starts to shift back towards the south, a little bit towards the north, and then December again towards the south. And then from December, it goes back up to January. So the winter months, you're getting more south, southeast, spring, a little northwest, summertime, fairly consistent west winds. And so in this situation, with all of these different conditions, if I were to design a wind tower, I would not orient it in one particular direction because that direction is going to change based on the year. A movable wind scoop like the Zion National Park building that can adjust seasonally could work, or you could have openings on multiple sides of a wind chimney. To find a windrose chart, there's you can find data if you're searching a certain look for data or historical climate data. Typically around airports will track the wind information because they're tracking that for the planes, and depending on which way the planes are going to land and take off at a runway. Airports typically have historical wind information. Keep in mind though, similar to say San Diego's climate zone 7, but we have the coast zone, which can be really foggy a lot of the year and cool. And then we also have Alpine or Ramona where it gets really hot inland. Wind can change very rapidly within a city or from one microclimate to another. That your wind pattern in Del Mar is going to be different from your wind pattern in Ramona. So if there's a regional airport that's near where you are, they could have some really good data. The other thing that you can do, especially if you're working on a project in a site that isn't very far away, you can go there and hang out at the site. And ideally, if you could do this multiple times over the year, which you don't always have that luxury for, you can start to get a sense of what the wind is going to do at that site. I worked on a house once for a guy and helping him do a fairly simple natural ventilation system where he just wanted windows in the right place and the inlet side and the outlet side and how to help him maximize that. But the homeowner, he was really familiar with his site. He's like, okay, we're on this hill, we're in Del Mar, we're facing west. All the time I've spent here, this wind is always coming from the water up over his site. He's like, I know this is just consistent. This is how this particular piece of property is going to behave. And so having that personal knowledge really to help me work with him to fine tune where to place those windows. Okay. So another project that I've worked on, I don't know how familiar you guys might be. Has anyone here visited the San Diego Children's Museum? Nope, it's downtown, it's on Island. Oh, sorry, my son's in the other room, he's laughing. He's like, I've been there. So this is a project I worked on, gosh, 2007 it was completed. So it's been a number of years now. I was the project architect on things. Was when I worked with Rob Quigley Architects. And we were trying to do a sustainable project as much as possible for the Children's Museum, which is a nonprofit. Have a lot of money, and everything was, you know, bare bones. But we had a really progressive client who was willing to take a chance and not put, when the building was designed, not put mechanical heating or cooling in all of the public gallery spaces. So in this case, South, right? And in downtown San Diego, 85% of the year, the prevailing wind is coming from the southwest off of the harbor. And that has a lot to do with the downtown location on the harbor, and Point Loma being the large mass of land that is protecting the harbor. Point Loma is really focuses all and helps provide the prevailing winds to always kind of come around the land and come across the harbor from the same direction fairly consistently. There's a few times of year when we get the Santa Anas and the wind shifts and comes from the east. I don't know if you guys have ever noticed this, but if I am going to go to the beach, I tend to go to Coronado because it's usually sunnier there than it is over in Mission Beach or Pacific Beach. Depends on the time of day, depends on the time of year, but again, it's that same, Point Loma is protecting Coronado, and the fog layers and they just lift faster because of the direction of the wind, gets rid of all of that moisture creating the fog, whereas the marine layer tends to get trapped and sit along the shore in Mission Beach and Pacific Beach. So we have a strong prevailing breeze coming from the southwest predominantly. We created a large open atrium type space and added what we called a cooling chimney to rely on the stack effect of cool air coming in low at the building, heating up with all of the people in the space, and then exiting out the top of the chimney. The other thing we're able to do because we knew where the wind was coming most of the time, we located the louvers on the north side and a little bit on the east side. So if you think of it with the wind coming from the southwest, more south than west, this is an upflow system. We want the air coming out of the top of the chimney on the opposite side from where the prevailing wind is coming from. In an ideal world, the chimney would have been placed more towards the north side of the building, but we were able to build the chimney because it's an extension of the elevator structure, which for circulation purposes wanted to be more centrally located in the building, especially near the 3-story atrium and the 2-story lobby. So not ideal for being the sole natural ventilation object, but the sole part of the design. So on the north-facing side, within the clerestory windows, we added operable awning windows to also let heat out at the top of the building. And I was going to say something. Oh, and like many other sustainable projects like the Zion National Park building, we're combining multiple different techniques here. So the north-facing clerestory windows, which work really well with daylighting, also provided a pitched roof facing south that was ideal for an active solar system. So there's photovoltaic panels on the roof of the south-facing bays. Now, one thing, again, this was a constraint of the design. There was some self-shading that it was occurring parts of the year where it would not have made sense to put the active solar panels on the whole roof because they would not get direct gain. So the active solar panels were located on the top third portion of the sloped roofs. So not just natural ventilation, but daylighting, active solar, combining a lot of different things together in one building. Okay. The other thing we were able to do in this project, which was super cool, is we had some design assistance sponsored by the California Energy Commission. So we worked with a UCSD physics professor who was, his fees were paid by the state to help. The program was to work with architects to promote low energy cooling systems. And we applied this project and were accepted into that program. So he was able to model the building and perform a CFD analysis, which is computational fluid dynamics, with a computer program. And we located where all of the openings were. And they suggested that after studying the airflow, if we added some more openings on the east side, in addition to the north clerestory windows, that would assist the system. Purple is, these are the big air intake on the south side. And I misspoke a little bit ago. I said north and east. It's predominantly east with a little bit of the opening on the chimney facing the north. It's been a while, I forgot the detail there. The other thing that they were able to suggest to us is, because we're cladding the chimney in glass to use the solar gain to help heat up the air inside to increase the stack effect. And they suggested that we put some black panels inside the glazing to help absorb more heat to increase that stack effect even further. And so we just took some corrugated metal, painted it black, and it's hung up at the top of the chimney. Kind of similar to a trim wall, where your south-facing glass has your airspace and then your mass or your dark-colored surface. That dark-colored surface is going to absorb and retain a lot more heat, and then it's going to re-radiate that heat to the air around it. So that's going to help heat up the air, increase the stack effect. More air will exhaust out the top, which in turn will pull more air in from the bottom. Again, it's that circular effect that once you get going, it's going to just keep circulating the air. So if it starts to get cold, and you want to keep the heat in the building, then what you want to do is close the windows, or in this case, we use roll-up garage doors, close those doors and don't let airflow come in at the bottom of the building. And so there won't be, it'll cut that cycle, that circle off, because there won't be any incoming air, so the air won't, the air can't leave because of the pressure differences. Brandon, you're looking very puzzled.
Yeah, I'm sorry. So you close the doors, and then that's, you don't have to close the chimney or anything because
Nope.
the pressure in the hot air takes in that cold air from the flow.
Yep, exactly. So the louvers at the top of the chimney are open 100% of the time. By closing the incoming air, you're stopping that process and just cutting that circle off.
I see. You're just not putting any input in it for that system to work.
Correct. Exactly. Okay. The same thing with the clerestory windows that these do actually close, and that's mostly for rain protection. But if this gallery here up at the top starts to get cold, by just closing that window, there won't be any place for the cool air to move to. So it'll still heat up in that space, but then the warm air will stay in the space. So, okay, so this is the computer model, and then these are just a couple of images of that CFD analysis. I saved this in a PDF, so these originally were actually little movie clips that would show the pressure changing around the building based on where the airflow is coming from. So that's what these little cardinal direction orientation is coming from. So right here, the wind's coming from the north, so they're looking at where it's creating all that positive pressure. The other thing, because we were in the downtown context, it was really important to model the other tall buildings around the site. And you can start to see, hopefully your screen's bright enough, but tall buildings often create those canyon effects with the wind that can increase in an urban environment, because that wind gets trapped between the buildings. And so looking at how that was going to affect our building was also really important. So this is kind of just fun little graphic images to catch your attention. The other thing I wanted to show about this building, and this is really interesting too, we did an analysis looking at the performance of different glazing with for the passive part of the system. Oh, I forgot to mention that. We're also passively trying to heat the building in the winter. So natural ventilation cooling in the summer, passive heating in the winter. All the floors are concrete with large things on the south side. And this image doesn't show it, but we were using deciduous trees on the south side. In the summer, the trees would block the direct gain coming into the space. So there is a little bit of an overhang, but instead of a large overhang preventing all of the summer sun, we were using deciduous trees. Let me see if I could draw a little tree. So that was out here in the garden, so here. Those where our trees are. When they were first planted, they weren't very so it didn't work very well, but over the years they have grown in significantly, and now they do, their effect at shading is a lot better. It's been interesting to watch the building over the years, and it's a little disappointing because it's not functioning. The clerestory windows aren't functioning as well as would be ideal. We used little automated window mechanisms to open and close them based on the computer program. And gradually over the years, they've just stopped working. Last time I was there, which was last year sometime, they had used 2x4s to just like stick up in the windows and just leave them open during the summer, and then they take them down during the winter. So that's a little frustrating, but it's also been a good learning experience. And I've seen this on other projects too. That project from last time with the gravity walls I was showing you, they had an extensive natural ventilation system with operable windows there too. Manual, automated window open and close are one of the trickiest things to get to work properly in a building. And there's several reasons for this. The architect has this great ideas like, oh, we can do this naturally ventilated system, and we can, you know, open and close things based on what the temperature is, and it's all going to work great. But here's the thing. It all comes down to the trades that are building the building. So you have your window guy. He knows how to come in and install a window in a building, in a wall. Okay. He doesn't know anything about automated operators. So you got to get somebody else who's going to come in and physically install the operator that's going to push the window open and close, which also needs to be wired. Your electrician and sometimes it's low voltage wiring, neither the electrician nor the low voltage subcontractor have any experience doing window operators. So you're trying to install a window, install an operator, get it wired, and then hook it up to a program that controls it. And the controls are also a very, very tricky part of the plan. Because generally whoever writes your controls program and monitors the computer aspects didn't install the window, didn't install the wiring, didn't install the actuator. So you have all these different trades that are all supposed to be working together to get part of a building working, and it's up to the architect. You would think the general contractor would make all these people work together, but they've probably never done this before either. And it's a case of, that's not my responsibility, that's not my job. And then as the architect, you're trying to get all these subs to work together and get the program to work right, and then commission it and test it and make sure it works. And it is a pain in the ass, which sucks because it's such a great idea. And it's so low energy intensive. And when you have a natural resource like a prevailing breeze, you'd really like to be able to do that. So automated windows, pain in the ass. People still try to do it. The technology does keep getting better, but at the end of the day, especially if you're up against a budget, keeping it simple. Just a window that opens and closes manually to let your air in at the bottom. And in this case, the 100% of the time open top of the chimney, that part of the system works great. The window part, not so hot. So, and that's the other thing, after probably a good 20 years of working on various different sustainable projects, the one thing I've learned is the more simpler the system, the more successful the thing is going to be, or the project will be, or the design is going to be. I got distracted though. The other thing I was going to mention is in working with the physics professor from UCSD, they did an analysis looking at different types of glazing on the building and how much it was going to heat up or cool down. If you recall, when I said if you're doing a passive solar system or Trome wall, you want to not use a low E glass, because you want that heat gain to come in at the time of year where you want it, and you want it to hit that thermal mass and store that energy. We analyzed low E double glazing, non-low E double glazing, and single paned clear glass, and looked at how they would perform at different times of the year. And the single paned clear glass worked the best in the winter to keep the most heat in the space. And so that's what we installed, which was great for the budget for the project because it's a lot cheaper. The only reason we were allowed to install that, though, because you can't, in California, any conditioned space, they look at the energy performance because they assume you're going to be air conditioning it. And so they're going to look at that performance of that glass and say, you don't meet the energy standards. So the only reason we were allowed to do this is the public areas of the museum are not conditioned spaces. And so they didn't have to follow Title 24 regulations of energy performance. Now, this is another key thing that happened on this project too, because it's a museum, there is no requirement for heating or cooling systems. Houses, office buildings, schools, the building code, California building code requires heating in certain types of occupancy, particularly residential, but then also educational and some other stuff. And so we just fell into this situation where we were doing non-conditioned space that allowed us to put in the single pane glazing, and per the building code for this occupancy for a museum, we didn't have to provide heating. There's actually no place in the building code that I know of that requires air conditioning, which is ironic. In terms of the South, you can't live in certain climates without air conditioning. But like Chicago, when they have a heat wave, and that's when all the people dies, because Chicago, you know, normally they're worried about heating in the winter, but they don't think about having cool apartments, especially low income cool apartments in the winter. So when Chicago has a heat wave and they're really worried about all of the elderly in small apartments where they're all cooped up and there's no airflow and no cooling, that's when people die from overheating. I got really sidetracked there. So that's a building code thing. That's not on the syllabus for the course, but to understand about how building envelopes work, that's what you need to know. There's not going to be a quiz on building codes. You get to learn that all on your own when you're working, or not on your own, but within your firm. You'll have plenty of time to do lots of code research down the road. Okay, I am like pretty much exhausted myself talking. Any questions? Not yet. Okay, we're going to get a little bit more in depth about like the Venturi factor and the Bernoulli effect on Friday. A little bit more specific about how air works and air flows, but not super technical. It's just going to be the next. This is like the 10,000 viewpoint of natural ventilation. Next week we'll get down to the 1,000 viewpoint. Does that make sense? 10,000 square feet up, you know, you're high in the air, you can only see so much detail. Friday we'll get a little bit more detailed. And I have to say, I did not get your assignments graded before class today. I apologize for that, but I will have them graded before Friday. If you turn it in, you're not gonna have any problem. And I did get the new assignment posted on Moodle today based on our passive systems we went over last week. So that will be due this Friday. Okay. If you guys don't have any questions, this is it for today. Thank you for listening to me ramble on. Mouse still not working. Oops.
Thank you.
You are welcome. And again, if you have any questions, please let me know. Trying.